I don't like spiders. Ah! Hello, gorgeous peoples. Yes, you gotta listen to me one more time. Fools! Alright, so today we're talking about nuclear energy, the energy that no one's scared of. And what we just want to give you an idea about is how do we actually make it? What the heck was that Albert Einstein guy talking about? E equals mc squared. Why do we like to make a bomb out of this? Big philosophical questions. So first, let's talk about how the energy actually gets extracted in a nuclear energy situation. It's coming from atoms, but the question is, how? What the heck is going on there? So let's show you. Here's this handy dandy diagram, and it goes that way. And what you're seeing here is nuclear fission. Fission means you're splitting atoms, unlike fusion, where you're combining them. So the atoms that they primarily use in a nuclear power plant are uranium. They are using uranium-235 atoms primarily. They also use other stuff, but for this purpose, we're going to just focus on uranium-235. And you get a lot of it. So the goal is get a buttload of uranium, ask North Korea, ask your friends, where can I find a lot of uranium? They're like, hey, I got some for you. So they put it in a big rod, and then what you do is you shoot a neutron into it. So here's our little friend neutron. I don't know how the heck you get an isolated neutron and you shoot it, but somebody figured it out, so good for them. And then it goes into the big uranium-235, and it goes to uranium-236, which makes it very unhappy. It's like, and it booms. It goes boom, boom. It splits. And what happens is it splits into a variety of products. The most important thing to note that it makes is energy. Freaking energy, people. Energy is everywhere if you look for it. It's right there. So that's what we want. That's the whole point. When you take really heavy atoms and you split them, you release energy. You also release other things, which we're not going to get into. But the most important other things that we want to talk about are it releases more neutrons. In fact, it creates 3 neutrons. And why is that important? Well, since the neutrons started the whole interaction, then if we have some more, we can keep, like playing online dating here. Like, hey, want to meet up? And so basically, if you cram a whole bunch of uranium-235, pack it together, when you split one of these uraniums, it will make 3 neutrons, which will then go and meet 3 other cutie patootie uraniums, and this process continues. And that is why we call this a chain reaction. You could start the reaction and it just keeps growing and growing and growing. All right, so there you have it. That's how you get energy out of an atom. And that's the end of the story. The end. Bye-bye. Your homework assignment is now go find some uranium-235 and try it at home. Super easy. Make sure you wear oven mitts. Anyways, it's not actually over. Now let's talk about how we can take this atomic process and blow it up. Hopefully not actually blow it up. And how do you actually magnify this to a large scale and make electricity, which is what we all want because we're electricity piggies. So here's a couple pictures of how they actually take it. So what do you need? You need freaking uranium. So yeah, obviously that's not easy to get, but people get it. And the issue here is if you have too much uranium, as you saw in the last thing, you create a chain reaction, and it could get so big that it's irreversible, and then you have skiddly diddly bop, boom, 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 and that's sad. Sad. We don't want that. We also are trying to make electricity and make freaking money, people. And so if you don't put enough uranium into the dang rods, then the chain reaction dies out because neutrons can't meet other uranium atoms, and then you get no money, and you get sad face again. All right? So what we need to do is kind of live a fine balance between having too little or too much uranium. Too little, you make no money. Too much, you destroy the world. So we got to do it right and hit right in the middle. It's like the 3 little bears. Mama bear, too hot, too cold, just right. We need it just right. So how do they set this up at the uranium at the power plant? Is they put the uranium in tiny little like these pellets, and so each little pellet on its own is not enough uranium to sustain like a long-term nuclear reaction. And then they put them in these rods. So here's a whole bunch of rods with a whole bunch of uranium pellets. And then you shove a whole bunch of rods together into like one giant grid. And then what they do is eventually you attach these rods, as you see in this picture, just, large pulley systems and connections and other rods that are able to lift in and out of the water. So they're going to put a whole bunch of uranium together. Each individual uranium pellet and rod is not enough uranium to make a boom boom. All right, it's not enough uranium to even make any money. If you had, it's going to kill you. I'm not going to lie. Don't stand next to the dang rods, all right? Just pay attention to the instruction manual. But it's not going to be enough to make electricity. So what you have to do is, if you want to keep it safe, is have each individual rod be unwilling or unable to actually create a nuclear reaction for a long term. But then you can combine all the rods together to start juicing the reaction up. And then if the reaction gets too crazy, then you can peel it back. We call the right amount of uranium to put into the reactor critical mass. So again, what determines how much energy is being made? Uranium, the mass of the uranium. That's the critical amount. The more uranium you put in there, the more potential chain reaction you're going to create, and the more energy you're going to make. Too much, you kill people. Too little, you make nothing. So we want the right amount, which is the critical mass. If you don't put enough in, then we have what we call subcritical mass. So each of these fuel rod cells, or fuel rods, are uranium that's subcritical. They can't sustain it on their own, but when you combine a whole bunch together, they can get to critical mass. If you put too much together, then you have, sadly, supercritical mass, and then massive death and tears, and say we didn't even have to worry about the Yellowstone supervolcano after all. Well, so here we have a little picture of a power plant. It's the power plant of your dreams. I know you were like, tell me more. Well, I'm so glad to show you. Steam. Oh my gosh, there's more steam in this reaction. We keep talking about friggin' steam a lot with energy. Again, a lot of times when we want to make electricity, we are taking a raw energy source and then trying to heat up water to make steam, which will turn a turbine and connect to a generator. So how do we do this with nuclear power? Well, here we have this lovely little diagram that makes no sense, but these little yellow things are supposed to represent the uranium rods. So what you do is you have a reactor. It's filled with blue stuff, which is Kool-Aid. I mean water. And that water is going to be bathing the rods. The rods, if you put lots in, are going to start making energy from their chain reaction. And the energy goes in the water. And then the water heats up, and it gets pressurized, and turns into steam. And then that steam is moved to a turbine to make generators. So what does the nuclear power plant need? It needs friggin' water, people. That's why most of them are near water all the time, because they're taking in water so that they can heat it up to create steam. Pretty simple process. Just like in a lot of other energies, you need to heat up the water to turn the turbine. If for some reason you have an issue and you're making too much energy and you need to tail it back, you could either remove the rods, so you can pull rods out of the reactor or away from each other, and that will slow down the chain reaction. Or there's these things called control rods, which are these little black things, and they're usually made of lead or other substances that restrict neutron movement between the other rods. And so you can drop these down in between the rods, and that will block the ability and slow the reaction down of the chain reaction. So here we are, we're pretty much done. So here is a bigger scale, a little bit further look at every little element in the nuclear reactor. And if we look, we've got our helmet here. This is the actual reactor. It's going to be lined in lead and reinforced so that if there was some sort of explosion in here where the uranium is, it's going to try and keep it in there, because if the uranium gets outside, it's like, ah! Chernobyl diaries and stuff like that. So we want to try and keep it in case there's an accident. So the uranium fuel is in there, the rods are in there, and this is where we make the steam. The steam goes here. Oh my God, it's another friggin' turbine, which is connected to a generator, which makes electricity. At the end, we just keep recycling this water. A lot of the times, though, we have more hot water than we want. Remember that we need to put the power plant near a water source, so it's usually next to a river or lake there, where it can intake water. And then after some time, it may not need all that water, so it will need at times to dump water back into the environment. And usually that water's clean. It's not radioactive or everything's fine. The only thing it is it's hot. And so that's why they have these things that are so ubiquitous with power plants. Is these are the cooling towers. So they're sending hot water through here to try and cool it off. And what comes out of here is steam. So it makes steam. So when people think of nuclear power plants and they think of like if somebody asks you what kind of pollution does a nuclear power plant think, most people think of radiation. They think, I'm going to have my eyes melt out of my head. And that's not true because nuclear power plants are running all around the world and this country and nobody's eyes are melting out of their head yet, all right? So when nuclear power operates correctly, there is no exposure to radiation because everything's contained into that reactor unit. What is the pollutant? It's friggin' heat, which is such a weird thing to say, but yes, what these power plants are doing is taking in cold water, heating it up, and then either dumping it back into the thing, and that could be a problem if you're a little fishy and you're like, I like it cold, I like it when it's really frosty outside. All right, and then they dump in scalding hot water, you're done. Remember, hot water is linked to low dissolved oxygen levels, so that would be a problem if you're a little fishy as well. And then it does release heat also in the form of steam, which is not really that big of a deal, but a lot of people forget that steam is a greenhouse gas. So some people, nuclear power is good because it's not releasing carbon dioxide, but it's not completely true that it doesn't release greenhouse gases. It is releasing water vapor. And with that, we're going to send you off, and we're just going to leave you with just a little bit of information that nothing ever goes wrong. No, that's not true. Of course this went wrong. Humans jack this crap up all the time, and we've jacked it up at least 3 major times. Time 1, Pennsylvania. Oh my God. I have relatives that live near this power plant. Could explain my behavior. Anyways, 2, that was in 3 Mile Island in the 79. Second time there was a major nuclear accident was in Chernobyl, which is in Ukraine today, but used to be USSR at the time. That was in 86. That is considered the worst of the bunch of the 3. And then in 2011, there was another meltdown in the 2011 Fukushima Daiichi plant, which is in Japan, and that was linked to the tsunami that occurred that year. You know, really good time feelings. I just want to send you off with like, nothing will ever be a problem. Don't worry, we're okay. Humans will figure it out. I love you. Bye.